Alright, this page has us look at more integrals of trig, but when I studied these four right here, the College Board does not require a student to have these memorized. Okay, so I'm just going to use this note card just to revisit integration with trig functions, but not with these formulas. So what that means is we're not going to do these two problems. I'm going to make up four of our own. Alright, problem number one. Alright, so there it is, 3 tangent of 2x times secant squared of 2x. Alright, we're looking for the antiderivative, so this is going to require u substitution. Alright, thinking back in our memory about the derivatives of the trig functions, okay, one thing we should be able to kind of recognize is that if tangent's present, try the option of thinking of tangent's derivative, which is secant squared, and it's present here as a factor. So that kind of gives you an idea of how to proceed. So I'm going to let u be tangent of 2x. Using the chain rule, the derivative of tangent is secant squared. Leave the inside function 2x alone, but multiply by the derivative of 2x, which is 2. We'll put that up front, and we'll put the dx behind here. All right. So looking back at what we have, okay, I'm going to have to bring in a 2, because I want all of this right here to be replaced with du. So if I bring in a 2, I need a 1/2 out here. Alright, so for my next step, I'm going to pull the 3 out also. It's a constant multiplier, so I'm going to have 3/2 integral, and then tangent of 2x is going to be replaced with u, and then this whole part of the integrand integral is going to be du. Right, to integrate this, just think of this as u to the first. This is going to be a reverse power rule just because of the way we set it up with our u substitution. So we're going to go back to 3/2, increase by 2 and divide by 2, and let's put the constant of integration outside. Alright, something we can do here is multiply the two 2's together, the denominator, so we're going to get 3/4 u squared plus c, and replace back in what u was. If you're ever not sure, you can always check your answer by differentiating using the chain rule. All right, let's take a look at another problem. All right, taking a look at this integral right here, I'm going to have to do a u substitution. U will be 5x. That derivative will be 5, not the 7 I have here. So probably what I'm going to do is I'm going to pull out that 7 first, so I can concentrate on integrating sine of 5x dx. So u is the inside function on sine, which is 5x. Alright, so let's bring in a 5 and pull out a 1/5. So 5 needs to go here and a 1/5 out here. Alright, and take it all the way to the u integral. 7/5 sine of, this is all u, and this is your du. All right, just notice the difference between problem 1 and problem 2. On problem 2, we have a trig integral, so we're going to have to use our integration background for trig functions. But on example 1, we put u all into a power function, so that's why we use the reverse power rule. It just depends upon what u is and how you proceed if you use the reverse power rule or a trig integration formula. All right, well, what does sine go back to? Well, it goes back to, not forward, but back to negative cosine. So I'm going to put the negative in front here with the cosine of u. Easy enough to put in 5x, and then your plus c. Again, you can check your work by differentiating to see if the derivative of this function right here using the chain rule produces this integrand right here. All right, example 3. I'm going to put it up here. All right, let's integrate sine of pi x divided by 4. So we know what u is. I'm going to go ahead and pull the pi over 4 out front as a pi over 4x as a multiplier. So the derivative is going to just be pi over 4 dx. Okay, so I need to bring in pi over 4, which means pull out 4 over pi. And let's convert to the u integral. So this will be sine of, all of this is u, and this is du. Alright. And actually what I'm going to do is I'm going to go back and put limits on this original problem. We're going to evaluate this integral from 1 to 4. So we won't need the constant of integration. So I've got 1 to 4 here. Alright, let's integrate. 4 over pi sine of u is going to go back to negative cosine of u, pi over 4x. Okay, and all that evaluated from 1 to 4. Right, so to finish this problem, we have some evaluation to do. Okay, when I go to evaluate, I'm going to kind of clean it up. I want to pull the negative 4 pi, negative 4 over pi out front. So all I have to do is concentrate on evaluating this function at the upper and lower limits. So let's plug in 4. So we've got the cosine of, and when x is 4, these will cancel. So it's really just the cosine of pi minus, plug in 1 for x, minus the cosine of pi over 4. Continuing to evaluate using our unit circle, we know cosine of pi, remember the unit circle? Pi is over here. Cosine of pi is -1, that's a -1, minus the cosine, or the x-coordinate, at this angle in quadrant 1 is square root of 2 over 2. Okay, you're finished. You could rearrange. You could show this in different ways. If I distributed the -4 over pi, I'd get positive 4 over pi plus 4 square root of 2 over 2 pi. And I could cancel here the 2 and the 4 and simplify that. Wait. Okay, so we're going to continue. We can simplify this if need be. Noticing that we have a common denominator, we could rewrite it as a single fraction, so we could put it all over pi. There are just many different forms of the answer. We're good here. All right, let's look at example 4. All right, so for example 4, what I've done here is I've gone back to our inverse trig functions. And what I mean is, if you go ahead and try and integrate this, if you try to use u substitution, you can see that u would have to be the denominator. The problem is the derivative would be 18x, and I don't have an x present here. So that approach is going to be out. So as we look at this, if we can't use u substitution on it, there has to be some other way to integrate this if we're asked to do that. So in our brains, if we can recall the inverse trig antiderivatives, this most closely looks like arctan. All right, so what we might want to do is, first of all, rewrite this to get it in that formula. Okay, right now the 3, I think I'm going to go ahead and pull it out front. That may or may not have been a good decision, but I'll figure that out later. So I have 1 on top. I could put the dx on top if I needed to. I'm going to rewrite the 4 as a 2 squared because I'm thinking it's arctan. Okay, and the 9x squared becomes 3x quantity squared. Okay. So at this point, it's looking like the arctan. Okay, so let me kind of put it back down here. I'm going to go ahead and stack the dx on top. Oh, that square should be on the outside. Oops. All right, so what we do for that integration formula is we identify what a is, and a is going to be 2. So if you don't remember what that formula looks like, you might want to real quickly look it up. U is going to be your 3x, and du is 3dx. So what that tells me is I need to bring in a 3. So I could actually just bring this 3 back in if I wanted to. Or if I wanted to bring in another 3 but pull out a 1/3, that would accomplish the same objective. So 3 here, 1/3 here, or like I said, you could have put 3 back in here and used that. Okay, so it looks like this cleans up to just 1. So the numerator is du. The denominator is going to be a squared plus u squared. This is exactly the arctan formula, so it integrates back to 1 over a, or a half, arctan u over a, so 3x over 2. And we want to evaluate that at 0 to 2/3. Okay, so now we just have some computations, some calculations to do. I'm going to pull the 1/2 out in front of the bracket. Okay, let's plug in 2/3. So 3 times 2/3 is going to give 2, but 2 over 2 is 1, so this is arctan of 1. And plug in 2/3, multiply by 3, and divide by 2, it'll clean up to 1. Minus arctan, plug in 0 for x, arctan of 0. So using these inverse trig integration formulas requires, if we're going to evaluate at limits, it requires that we revisit the unit circle. All right, so what angle has a tangent ratio of 1? Well, arctangent is defined in quadrants 1 and 4. Okay, so the appropriate angle having a tangent value of 1 would be pi over 4. So pi over 4 minus what angle has a tangent ratio of 0? Well, that's going to be right here at 1, 0, where y divided by x gives 0. And cleaning it up, we're going to get pi over 8. Right. So just using this note card to revisit some trig integrals and revisiting the derivatives, etc.